This is my final physics project, and I will be constructing a Gauss rifle and mapping out the final velocity of the exit ball bearing and comparing the speeds depending on how many magnets are put on the platform. And this may not make sense, so I'll explain to you guys what a Gauss rifle is. So a Gauss rifle is essentially a magnet that has two ball bearings attached to the end of it, and this magnet is actually quite strong. So you have a trigger ball which accelerates rapidly towards the magnet, and as that ball accelerates and it comes in contact with the magnet, the um, ball bearing on the outside, which is it's still attracted to the magnet, but not as much as the ball right next to the magnet, is able to be released at quite a high exit velocity because the trigger ball bearing is accelerated quite rapidly. And as you add more magnets to this, it can actually increase the final velocity. So I'll show you guys this in action. So there you guys kind of saw how it worked. But in order for it to work, I had to build a platform for it to be conducted on. So here's kind of a time lapse of me building this thing. It wasn't too hard. I basically just kind of sawed a few pieces. Then I tried to screw it on, but I realized that it wouldn't work with the screws we had, so I just kind of decided to just hammer some nails in there. It wasn't anything like too hard. The final product kind of looked sloppy, but I mean, it worked well and did the job for what I needed. Yeah, there's kind of the final product. Okay, so for this experiment, I kind of made a little procedure to follow. And so what I originally was going to do was just build the platform for the experiment, to take place on. Then I was going to film the experiment with one set of magnets all the way until 5 sets of magnets. And then analyze the videos in Logger Pro, create some graphs from the videos, and then eventually use that data to then find a difference between the calculated variable or calculated final velocity and the measured value of the final velocity of the ball bearing. And the difference between the calculated was that the calculated value is simply can be found from using the conservation of momentum equation, and while the measured value is just the value found from Logger Pro. And I'd use the data to eventually create a graph so that I would be able to predict the final velocity of that ball bearing uh, with any amount of magnets, not just 1 through 5, which I tested in the experiment, but if I had wanted to see what the final velocity was 6 magnets, I could also get an estimate at least from the data. So some of the data that I had to collect was the weight, or sorry, the mass of the ball bearing, as well as the set of magnets and ball bearings together. So the set was 28 grams, while just the ball bearing itself was 8.5. But because my scale was not accurate, I had to measure it and get an average with 2 ball bearings, just to make it a little more accurate. And though together they weighed 17 grams, so I just said that each one weighed 8.5 because the scale couldn't really go into decimals, so I just found that way a little bit more accurate. So with that being said, I finally moved on and started doing data with just one set of magnets. And that is shown in this clip right here. Okay, so this is going to seem a little confusing at first, but this is the data I got from analyzing one, or just the data from one magnet. Um, and as you can see, I found the calculated value of the final velocity using the conservation of momentum equation, and that's shown up top there. And basically what I did is I took the initial velocity of the ball as it's about to hit the magnet after it's accelerated, and I took that data from Logger Pro, and I then um, added that plugged that into the equation, and then I also found the final velocity of not the ball bearing, but the set of magnet or the magnet and the two balls attached to it after, because there was a little bit of recoil. So you have to account for that in the formula, and that recoil there shown was um, negative 0.534 meters per second, so actually pretty decent. But then I was use that data to find the final velocity, and in that case it was 2.15 or 2.12 meters per second, and then I found the measured value to be 2.07 just from Logger Pro, and I did a percent difference, and actually the percent difference was quite low on this one. It was only 2.399, so actually fairly accurate, which is nice. And then, as you can see, I just had more pictures and graphs from the data in the next slide, but I'm not going to show this data for each magnet just because I feel like it'll be pretty repetitive. But yeah, so this is the graphs that I found. Nothing too important here, just that the velocity stays relatively constant, slowly decreasing over time, probably due to friction. I have like a picture from the Logger Pro in there too of the data. And then as you can see, position and time, it just slowly increases. And then over time, from the three graphs, one of the recoil, one of the final velocity, as well as the ball as it's accelerating towards the magnet too. So next up we have the ball with two magnets this time. So this is the calculated value from two magnets, 2.075 meters per second, as well as the measured value, 2.88 meters per second. And then using the percent difference, it's a massive percent difference. As a matter of fact, the calculated value on this one is actually less than the one with one magnet, which just seems logically incorrect. So probably some error there, probably having to do with initial velocity being 2.03. That just seems a little low. I assume it's probably something to do with my camera just not being able to capture enough frames or something like that. But other than that, graphs kind of seem similar to the one before it. Yeah, so next up we have three magnets. Yeah. Okay, this is the data from using three magnets on the Gauss Rifle. So as you can see, our calculated value was 3.254 meters per second, and the measure value being 3.305 meters per second. So very close, only a percent difference of 1.56. And the general trend between the different sets of magnets is the final velocity is actually increasing. Um, and as you can see from the graphs, the velocities, they're staying pretty much straight, which is good. Slight decline due to friction, but and then the initial velocity is accelerating. So, but or yeah, and then position and time graph of the three different data points plotted. Yeah. So now moving on to four magnets. Okay, moving on to data from four magnets. This time, as you can see, the velocity still increases. Calculated value of V of F being 3.51 meters per second, while the measure value is 3.9 meters per second. Percent difference 10.44%, so not too bad, but it could definitely be more accurate. Nothing too different from here either. Um, yeah, so kind of moving on to the data using five magnets. Okay, this is the data using five magnets. As you can see, the measured value of EF still increases. This time it's at 4.86. However, the calculated value way lower is 3.105. I don't know how that happened, but think it again has to do with the initial velocity only being 3.1 is just not accurate at all. However, I think it's to the fact that my camera's bad and it can't really capture it to its true initial velocity just because the frames per second are too low. So the percent difference again here is massive, 29.6. So, but there's nothing we can really do about that, or nothing I could do. So, yeah. Um, Moving on, I just have some more pictures from the experiment in this next slide. Okay, so in this, I would like to talk about the possible source of error, that could have led to some faulty data. First being the bad camera, which I talked about before, it would have helped with accuracy on the initial velocity and just overall better accuracy in Logger Pro. I had a short track. I think it would have been accurate better if maybe I had a better track or if it was longer too, because I feel like the um, magnets kind of got cramped almost. So it was kind of hard to track the data. The next being frictions, or the final ball bearing before it's released, is attraction to the magnet and air resistance. Those all slow down the final velocity, and I'm not able to really track them. So that can also lead to error. So that kind of sucks. But also the low amount of trials, I wasn't able to do a large amount of trials just because the amount of time I would have to spend on Logger Pro would be days, and that would be hard. As well as also when I was building this thing, I put some nails, to hold it together, and I realized the magnets actually attracted to the nails. So sometimes the ball would kind of almost get attracted to the nails, which was not good. It would kind of screw up some of the trials, so I kind of had to redo it. But other than that, I mean, everything was pretty good. Yeah. Okay, this graph is really important. This is kind of where everything kind of comes together. So right here, this is a graph of the final velocity of the ball bearings um, um, measured over how many magnet sets I use. So basically what this tells me is I can get an average slope from this data chart, and for example it was zero point 0.5 or 0.5252. So what that means is for every increase in magnets, for every increase in magnet, basically the final velocity of the ball bearing will increase 0.5252 meters per second. So I can use this graph right here to predict the final velocity for really any amount of magnets. However, I did just put in there, be careful for extrapolation, because of course if you say this data probably won't be accurate if you're using 100 magnets. But yeah, other than that, um, this was my project and I hope you found it interesting.